Okay, I apologize. This video just jumped into a few more videos because I was interrupted by an announcement made over the intercom. So let's talk about graphing a piecewise defined function. There's a number of ways you can do this. You could just think about all the values that are less than 1, and we could plug a bunch in, and then we could plot them, and we could graph them. And then do the same thing for x is greater than 1. We could graph 2x minus 5, right? Start down here on our y-intercept and use its slope, graph the line, and then erase whatever part is outside of our domain. But I found that the easiest way for students when they're starting with these is to kind of build the barriers and then work off of those. So for example, this one, the domain is kind of a barrier at 1. So the first function exists where x is less than 1, so on the left side, and the other one is where x is greater than 1, so on the right side. So I'm just going to draw this line in. This really has nothing to do with as far as my final graph drawing, but I'm just going to draw a little dashed line. That's my barrier, so one piece can be on the left of it, the other piece has to stay on the right. They can't overlap. Then we can just start to graph. Now again, if you're really comfortable with linear equations and this right is like my y-intercept, and this is my slope, I can use those pieces to graph. I start on the y-axis and I go down 1, 2, 3, 4, 5. I'm going to put a little point there. I then use the slope, which in this case is 2 or 2 over 1, and I rise 2 from that point, 1, 2, and over 1, or down 2 and over 1. Now again, I can't keep going beyond the barrier, so you stop there, and it looks to me, because this is just a less than right here, we're going to do an open circle. So we're going to put an open circle and then connect that line headed that direction. Now, if it's crossing the y-axis, the y-intercept is pretty easy to use, and the slope. The further it gets from the y-axis, that's a little more challenging. So another way to do it is we just plug the value in, and it tells us where to start at the barrier. So if x is 1, I just come over here and plug it into my piece. And it'll tell me where to start my second piece. So if I do negative and I plug in the 1, negative 1 plus 7 is 6. So I'm going to go on my barrier. I'm going to go up 1, 2, 3, 4, 5, 6. And I'm going to put a closed circle. Now again, it's closed because right here by my domain, it's greater than or equal to, and that or equal to part makes it closed. From there, I just use the slope. So we know how to draw lines with slope. Look out front of this guy. There's just a negative there, which means it's a slope of negative 1. So I'm going to go down 1, right 1, down 1, right 1, down 1, right 1. And oops, I drew a little line there. Then I connect it headed that direction. Now again, we just, our last step here is ask, does this pass the vertical line test? So we always want to make sure when we're done that our pieces stayed within their barrier bounds. So notice if we draw vertical lines here, right, it only touches that function. If I draw them up here, only touches this function, and it still passes the vertical line test because it touches that one there, and then this one's an open circle. So there's no overlapping pieces on these. And we can identify those two separate pieces there. Let's look at example 6. So we're kind of going to do the same thing, and I'm going to use the idea of plugging it in. But first I'm going to draw those barriers. So notice here this first barrier or domain restriction is going to be where x is negative 2. So there's x is negative 2. Then notice the next one goes from negative 2 to 3. So the next piece is going to lie between the negative 2 barrier and a barrier at positive 3. From there, again, that other one is just going to be on the right of positive 3. So let's start to graph. So again, if I want to do the first piece, I'm going to take its domain value and plug it in for the x value. That way I know where to start on the barrier, or in other words, end on the barrier. So I'm going to do 1/2, and I'm going to plug in the negative 2 plus 3. 1/2 multiplied by negative 2 is negative 1 plus 3 would just give me 2. So I'm going to come over here, and on this first barrier, I'm going to go up to positive 2, and I'm going to put an open circle. Again, it's open because this is a less than sign, and it's not or equal to. Then I use the slope to help me out. So if we look at the slope here, it's 1/2. So we come over here and it's tempting to go up 1 over 2, up 1 over 2, but recognize you just went into the wrong barrier, right? This guy's domain is restricted to this left side. So instead of up 1 over 2, I'm going to go down 1 and left 2. And notice that makes the same line, but it heads out this direction, okay? So when we graph that, we're going to go down 1 over 2, down 1 over 2, and we're able to plot this line. Oops, sorry, that's terrible. Then we go to the next piece. So notice on our middle piece, it's sandwiched between -2 and 3. So maybe I start with the -2. If you plug that in, right, you have a negative, so that's just a +2. So on this left-hand barrier, it actually fills this circle in because it's also at +2. Then we could do the same thing with the right-hand barrier. So this 3, plug that guy in here. And if I have negative and I put a 3 in there, I'm at -3. And again, he's an open circle if you look at that less than sign. Because we know that's linear, that's just going to connect here. Now, again, if I didn't want to use the ends of my barriers, that one crosses through the y-axis. So you could look at it and say, well, the equation there was -x. So again, my slope there would be -1, which looks good. It's going down 1 over 1. And there's no y-intercept listed, so that means that's 0. So it looks like we did good. It's going through the origin, and it has a slope of -1. And it's staying within its boundaries, so that's perfect. Then we go to the last one. I'm going to choose a different color so we can actually see it. If I plug in its domain value so we know where to start, we're going 3, and then we plug in that 3. So we get 9 minus 7, which is 2. So on this barrier, right, when x is 3, we're at 2 with a filled in circle. And notice its slope over here is a +3, right? Or in other words, 3 over 1. So we're going to rise 3 and run 1. So up 1, 2, 3 over 1. And then the other one's going to go off the graph. So we'll just draw our arrow headed up that direction. Again, the last question we ask, does this pass the vertical line test? So we go like this. Yep, that guy stayed in his barrier, this one stayed in his barrier, and this one stayed in its own barrier. Lastly, you're going to be asked to identify the domain and range. Now recognize domain and range. I know sometimes we just do what our teacher tells us and write -infinity to infinity, but these are going to require that you actually think about where your graph exists and where it doesn't. So as far as the domain, right, domain is like what x values from clear out here in -infinity, where does your graph exist all the way to infinity? If you could tell me what values it existed for. Well, notice there's an arrow headed this way. So there's no limit to the negative values it could go to, so we actually are going to start our interval at -infinity. Then we look in here, there's no breaks, right? There's no spot where our graph doesn't exist, because even this spot right here, the hole fills in where that hole would be. So we're just going, and then this arrow is going to head to the right. So even though it's only slowly going to the right, it will continue forever. So again, our domain is -infinity to infinity, or all real numbers. Now, as we look at the range, we look at bottom to top. So again, notice there's an arrow that's headed down. Now it's not headed straight down, but it is definitely going down. So all y values will be accounted for. This one's going up. All y values will be accounted for. And then where we can actually see the graph, it doesn't look like there's any holes. It doesn't stop anywhere. So this range is actually also -infinity to infinity. So that's one that would look like that. If we go back to example 5, so let's do the same thing with domain and range here. Notice that your domain, again, you have an arrow pointing in the left direction and you have one headed to the right with no holes on the inside. So you can say -infinity to infinity. Another way that I like to look for the domain is you can also look over here at your domain restrictions. Notice this is all x values less than 1. This is all x values greater than or equal to 1. So there's really no x values left out ever. Everything less than, everything bigger, that's all x values. For the range, we're going to look at the graph. You'll notice this arrow's going down, so is this one. So for our range, we're coming from negative infinity down here, but then our graph is actually going to stop at positive 6. So we're going to say negative infinity up to positive 6. It's a closed circle at positive 6, so I'm going to use a bracket, and then we always use a parenthesis with infinity. Now I'd be done. That's my domain, that's my range. And we're going to practice with that a little bit and see how it goes. Okay. The very last part of the notes I'm going to go through rather quickly, but absolute values can be expressed as piecewise functions. They're essentially just two pieces, right, connecting at what we call the vertex. So if you look at our parent function here, right, f of x is equal to the absolute value of x, you have a line that has a slope of positive 1 headed this direction. If this was kind of our barrier, then you have a line with a slope of negative 1, right, coming this direction. They both have that intercept of 0. So if we were to write their equations, right, a slope of positive 1 with a y-intercept of 0, that would be like this right here, positive 1, and that occurs again on this side of the boundary at 0. The other one has a slope of negative 1, so you see him over here, and that's where x is less than 0, or on the left side of 0. Okay. There's a couple questions on here just to think about. It says, comparing the piecewise function to its graph, why would an absolute value function always have one piece with a positive slope and one with a negative slope? Remember, absolute value functions always make a v, so there will always be a positive slope and a negative slope. Or if it's upside down, this guy's the positive slope and then a negative slope, but there's always one piece of each. And notice if we were to look for that barrier, that relates to the vertex every single time. Because if the vertex moves on the, and I'm going to draw a little graph on the right hand up here, if it moves over here, now that barrier or that domain restriction is that guy right there where it's meeting. If it moves up here, right, so let's say our graph's up here, this is the domain restriction. So no matter where it moves, it doesn't matter if it's going up or down, but that x value where your domain is relates to that. So if we're talking about how does the vertex relate to the domain, we're always going to be looking at that h value to help us with that. So, right, if our vertex is like that hk, this guy right here is going to help us with our domain restriction. So we're going to use that value. Okay, so let's see if we can write one in absolute value form. So again, here's our function. I'm going to think about it as, right, here's my domain restriction, and I'm just writing the function. First of all, in absolute value form, we were getting really good at these. This one, I'm going to count its slope, so I'm going to erase that line for a minute. If I count the slope, it looks like we're going right up 1, 2, and over 1, up 2 over 1. So that would be like 2 as my slope. Then the absolute value bars, right? It doesn't look like it moved anywhere, so it would just be a slope of 2, didn't go up or down or left or right. So as a piecewise function, again, you're going to have two pieces. So let's maybe just call this f of x. And one of them has a positive slope, so this one going to the right. Notice it has a positive slope. It's headed that direction. And I'm going to write it as the second piece, but it's going to be 2x. And again, our barrier's at 0, so this is when x is greater than, and I'm going to include it, or equal to 0. It's on the right-hand side. We could also then look at the left-hand piece of our v, and notice it just has a slope of negative 2, so it's doing the exact opposite, right? Down 2 over 1. So we're at negative 2x, and this piece exists on the left side of 0, so when x is less than 0. And that would be the piecewise function that would represent the v, or the absolute value function. Okay. Let's look at one more. Again, they can shift left or right, up or down, but essentially we're going to use these same pieces, so I already drew a lot over it. So again, you're going to look over here and notice your domain barrier, right, is right there at negative 3. It's that like vertex right there. So if I first of all want to write this with absolute value, I am looking at the slope. Notice it's going to go up 1 over 1, up 1 over 1, up 1 over 1. So we can see as a slope of 1. So we're just going to say, oh, sorry. You can put a 1 there if you want, or I'm just going to draw the absolute value bars. It looks like it moved to the left 3, so we're going to say x plus 3. And it looks like it moved down 4, so we put subtract 4. Okay, that's our vertex form of the absolute value function. As a piecewise function, again, we're just going to write this as a function, and it's going to have the 2 pieces. Now you can do the right side or the left side first. It doesn't really matter. A lot of times we'll write them left to right. So if I do this positive 1 headed this direction, right? Essentially what you do is you just take that equation that we wrote, y equals absolute value of x plus 3, and you do a positive version of it. So on the right-hand side, it's like having x plus 3 minus 4, which is just x, and then we combine the 3 minus 4, negative 1. So I know that on the right-hand side, my equation is x minus 1. Again, you can check that. Your slope is 1. It's crossing at negative 1. That looks perfect on our graph. So that's on the right-hand side of 0. Then we do a negative version also, just like when you solve absolute values. So we do negative x plus 3 minus 4. Notice that negative will distribute in here and affect those values. So we get negative x minus 3 minus 4. So negative x subtract 7. This piece is an x minus 7, and that piece exists on the left side of, not 0. I apologize that I wrote 0. Again, look at your barrier, and this one moved, so it's over here, right, at negative 3. So this is on the right side of negative 3. This is on the left side of negative 3. So the way that it's written, if you look up at this formula, right, is just saying, notice there's a positive piece, and then there's a piece where we let the a value or the slope be negative. If I were writing this, I would probably write negative a and then x minus h plus k. It's the same thing, they just put the negative inside a bracket. So we're going to practice with that a little bit. Again, you can always check your answer. If you're unsure and you're like, does that really create my v? Well, let me look. Let's see. Oh, yep, it has a slope of negative 1, and if it kept going, it would certainly cross at negative 7. So there's the negative 7 that I wanted. Okay, always kind of double check your work there.